This is the Niometrics web interface. Here we have the launchpad with all our solutions. For this demo, we will be jumping into X-Analyzer. X-Analyzer is used by telcos to identify, inspect, and analyze network events across the control plane. There is an easy-to-understand visual breakdown of interfaces within telco control plane traffic. We drill down to see a breakdown of procedures, and for this demo, we will be selecting the Create Session procedure on the S11 interface. Let's click on the User Authentication Failed cause code. The chart now displays the frequency of errors in half-hour intervals. By clicking on the most recent bar, we drill down to a 1-minute interval level of granularity. X-Analyzer quickly loads records of every error that occurred during the interval for, in this case, the User Authentication Failed cause code. We can then select a specific occurrence and user, and then run a trace on that event, transitioning from the X-Analyzer workspace to the tracing workspace. Both of these workspaces can be used together to isolate any specific packet from any unique subscriber out of the subscriber base of a telco and the billions of packets that are sent across their networks daily. At the center of this screen, we are seeing the Create Session response message, the red on either side indicating that an error has occurred. Here, we see the messages associated to this specific subscriber and a mix of interfaces and protocols around the time when this error occurred. Up the top, we can see the nodes and addresses that are involved in this communication stream. This button on the left lets you add filters such as protocols, interfaces, specific message, and cause code value. It is easy to download a PCAP file containing the packets associated with the messages in the current view. We can then open this locally with Wireshark or any other packet tool for further analysis. This workflow enables network engineers to focus on a few packets, to mitigate issues that potentially impact millions of subscribers.
Hello everyone, my name is Lazaros Koromilas. I am with Niometrics and I'm gonna talk about capturing, storing and receiving packets in big networks. The talk is structured like that. We're gonna talk about the technologies we use in the company. I'm going to give you some numbers indicative of the scale of things we're talking about. Then we're going to follow a packet through the system and see the various stages of processing. We're gonna see how we write the data, what metadata we're logging with them, and of course the access path. The domain is telco. We tap the core of a telecommunications company infrastructure and observe the packets going through. We decode them and we produce a series of logs. On top of this engine sits an analytics pipeline which uses those logs and produces aggregations, performance indicators, and other statistics. Now the question here is, why do you also need the packets themselves? And the answer to that is that packets are still useful to the network engineer for troubleshooting and investigating specific scenarios. And these packets are the packets on the control plane. Now about technologies. The typical probe we deploy in production is a multi-core Xeon with 2 or 4 socket server. For receiving the packets to our user space application engine, we use DPDK, and there it sits a code base of decoders written in C that handle most of the protocols protocol stacks in mobile, from 2G, circuit switched voice, 3G, LTE, VoLTE, IMS, 5G now, and we also handle fixed broadband protocols, control plane, which is radius and DHCP, but the rates there are much smaller. Now for metadata logging and indexing, we use a time series database which is also developed in-house. And all this together is packaged and accessed through a web-based application, the one seen in the demo. Now some ballpark numbers. The single probe performance we can handle, throughput we can handle is 100 gigabit of user plane traffic. Actually 100 gigabit of traffic, a small slice of that is going to be control plane, most of it is user plane. So for example, 1 gigabit per second could be the control plane in this case. And in terms of packets per second, this is going to be a million packets per second of control plane traffic. And this more or less is in par with a million subscribers. Not all of them active at the same time, but still that's the size of the user base that a probe covers. Now the average telco has tens of such probes deployed across their sites. And the average packet size on the control plane is going to be around 150 bytes. If we do the math here, the control plane alone in a telco like that is going to be hundreds of terabytes daily. This is how a probe looks like. We have ports that receive packets and threads that receive packets off of those ports. Can have 2 threads receiving from the same port, for example. These received threads apply a flow hash on the packet to decide which worker is going to be responsible for that. So for example, if a packet comes in from port 0 and goes to receive thread 0, this thread will decide that it goes to worker 3. And this is where the decoding takes place. This worker is going to produce message entries about this packet and populate them with metadata and submit everything to a dumper thread. This dumper thread is going to collect many packets in a batch and write them to a disk into a pickup file. When this is done, the dumper determines at which offset this packet was written to the file and fills that into the metadata entries, gives them to the logger, which pushes them, this is another thread, and pushes them to the time series database we were talking about before. Now, this database can be on the same machine or on a machine nearby. It's going to be on the same rack anyway. So the distinction between a packet and a message. A packet may contain multiple messages. For example, in the SCTP protocol, we have multiple chunks, and these chunks carry data that can be unrelated. Kind of a combining mechanism. The other way around, we can have a large payload diameter message, for in this case, which needs multiple TCP segments to carry it. And IP fragmentation could be similar. Now, how we write the data. From now on, we're going to be talking messages. So the decoder submits the packet with the list of messages that it contains to the dumper. When a batch is completed, it goes to disk. We determine the offset of each packet, call a callback for each message of each packet, and then set everything to the logger to go to the database. The logger pushes all these entries to the time series database. Most of them will have a subscriber ID filled in, and this ID is how this record is indexed in the database. If we have it good, they get logged right away. If a message doesn't have an ID, it's buffered for a certain amount of time because there's a chance that we might learn it soon, and we wait for other messages of the same session with a valid ID to get this with them. This is an example entry. We see that we have microsecond granularity in the timestamp here, the ID, we have the message protocol, the interface. This triplet here is responsible for recovering the packet, so it tells us which host it's stored at, the file name and the offset. Furthermore, we have some extra positioning of the message inside the packet, position and size, source and destination addresses and names, some extra metadata that are protocol specific. So for example, for this GTPC version 2 protocol message, we're gonna have a procedure type, a code, a code value, some extra metadata. This is all useful for producing a meaningful description of what this message is about, and the session ID. Now about the access path querying, how do we get message records back from database? We say that we need to get a message for this subscriber ID and the time duration. So the database responds with these 3 entries. We see that the first 2 have the same timestamp, they have the same location, let's say, because it's the same probe host, the same file and the same offset. So this is basically the same packet. The only thing that differs is that the messages are positioned in a different offset inside the packet now position. The third entry is unrelated with all this, and it even comes from a different probe. So we see here that there are cases that a subscriber is covered by 2 probes at the same time, or to express it better, through his through moving from a cell to another in the mobile infrastructure. At some point it crosses a boundary where it goes from the territory, let's say, of one probe to another. So when we serve this data, we merge from multiple probes. To conclude, we saw a system that records packet at rate reaching 1 million packets per second, that means that we have a database that can handle such rates as well. Its record in the database is self-describing and points to the packet so we can recover it. The database is optimized for selecting records linked with a specific ID, so it's indexed by the ID. And the value of all this is that we can investigate specific scenarios, and the network engineer can have control plane tracing and focus on very specific types of messages. Thank you for your attention.
Very interesting speech, technical, but that's what we're here for. So it was very interesting to hear what you had to say about indexing and packet management. Tell me about your company. Is it a new one? How long have you been in the market, your company, and you? How long have you been there?
3 years and a half now since I joined. The company is more than 10 years old, although the presence it's present globally, and right now not in Europe. Yeah.
Okay. Well, we have a question in the audience from a young student entering IT, and I would like you to give some advice on which technology to dive into, relating to what you're interested in and you're working with.
By looking back into my path, I can say that it makes sense to find open source projects that have visibility and impact. Try to read the code, contribute. DPDK is a good project to look at if you'd like to go for C code basis. Operating system kernels are very interesting code bases as well. I would point to OpenBSD because I love the system and it's clean code. And yeah, or I don't know, Redis I hear has a good code as well, off the top of my head.
Okay. Very interesting stuff, cool stuff. Thank you so much. We appreciate your coming here and introducing your speech, and also being our sponsor, your company. We really appreciate that as well. Thank you so much. Thank you for coming. And we hope to see you live at the next event. We would really love that. Okay, so enjoy the rest of the weekend, and thank you so much. Have a good day.
As well.